In today's session, I will be covering C2.1 in the OCR spec, which is atomic structure, isotopes, and ions. This topic underpins a lot of content in chemistry and underpins a lot of theory behind chemistry. Just to kind of run through what's going to be covered in the session, we'll start very quickly by recapping atomic structure. We'll then look at the role of protons, electrons, and neutrons. Understanding relative atomic mass from the periodic table. We'll study something called electron shells in a bit of detail. And eventually we'll apply everything we have learned to ions and isotopes. So I hope you find today's session useful. You will need a periodic table, a GCSE periodic table to hand as we go through. Without further ado, let's go. To begin with, the current atomic structure that you studied in GCSE is a step up from what you may have looked at Key Stage 3. And it essentially consists of something called a nucleus with usually a ring outside. If we label this up, the center is known as a nucleus. It's right at the center of the atom. And then we have electron shells around the outside. At GCSE, you need to appreciate, and also at A level, that there are multiple electron shells, not just the one. We'll talk about electron shells in a bit more detail later in today's session, but this is probably what you have come across in recent months and years, where the X's represent electrons. Now, within an atom, you have what we call subatomic particles, and sub meaning smaller than, atomic meaning smaller than the atom, and particles meaning particles of matter, or bits of matter. And the three you should be familiar with from your time of science are protons. You should be aware of electrons, and you should be familiar with neutrons. And if you aren't, just to kind of recap that for you, protons have a positive charge, electrons have a negative charge, and neutrons are neutral, they have no charge, so we can ignore them. And actually I have to put a line like that to make it unambiguous. In addition, you need to know about the relative mass. And what that means is in comparison to one another, what is their mass? Makes it quite easy. Protons have a mass of 1, neutrons are also 1, so they are actually equivalent in mass. Whereas electrons are much, much smaller in mass. So much that usually we can say they are negligible. Yeah, they are 2,000 times smaller in mass than a proton. Importantly, that doesn't affect the charge. One proton will still attract a single proton, vice versa. And the last bit of information we need about subatomic particles are their location. And you may recall this, you may not. Protons are found in the nucleus. Neutrons are also found in the nucleus, whereas electrons are found outside the nucleus in what we call shells, which are these shells up here. If we go ahead and add on that information, what we find is electron shells contain electrons only. That's an important point actually. Symbols we're going to use from now on. Electrons will be represented with a small e and a negative charge. Protons will be represented with a p and a positive charge. And neutrons with an n and a 0. And those are the symbols we're going to use. The nucleus, on the other hand, contains both protons and neutrons. And it follows that this is equal to the mass of the atom. Because as we've already said, electrons have almost zero mass in comparison. It's very negligible in comparison to protons and neutrons. So if we wanted to weigh this atom, most of the mass would come from the nucleus, down at the bottom. That's an introduction to protons, electrons, neutrons, and the atom. And you will have to use, be able to, be confident in talking about protons, electrons, neutrons, and calculating them from the periodic table. That rather neatly leads us on to what we call relative atomic mass. Now, if you turn to your periodic table, and you've probably seen it before, in general, most elements are represented in a box with a symbol, which I'll use X to represent currently. And then there are two numbers, which I'll represent with the symbols A and Z. Now, it's important to note different periodic tables will have different variations of the numbers. Some of them will have Z at the top, some of them will have A at the bottom. What do I mean by A, Z, and X? If I just go ahead and give you the general format for the periodic table, this is what it looks like. X represents the symbol of the element. A represents what we call atomic mass. And I'll add in relative atomic mass. And as the name suggests, it tells you the mass of an atom, of an element, compared to an atom of carbon-12. Now, this deliberately is not the actual definition you need for GCSE because to understand the true meaning of relative atomic mass, there is a concept known as the mole, which comes up in year 11. And actually, it's quite a tricky concept to understand at first. But once you do understand the mole, it's deeply fulfilling. It actually changes everything. You get a deep sense of satisfaction. So more of the mole in later years. For now, we can just think of it as mass of an atom of an element compared to an atom of carbon-12. And then the smaller number tends to be what we call the atomic number. Now, just to kind of break this down a little bit further, there's the bit we're actually interested in, is how does this relate? There's a very easy way for you to memorize which one's which. The relative atomic mass is always the massive number. And the reason why I'm saying massive here is it's the bigger number. So it doesn't matter which way around you have A and Z, the bigger number will always be the atomic mass. And what does it represent? Well, as we mentioned already, protons and neutrons equal the mass of the atom. They make up the mass of the atom. So relative atomic mass is a measure of protons and neutrons, the number of protons and neutrons in your atom. Notice there's no mention of electrons because electrons have negligible mass in comparison, which means the atomic number is the number of protons in the atom. It's often also called the proton number as a result. And my last point here is only in a neutral atom, the one which has no charge overall, this number also equals the number of electrons. Let's move straight into an example. So I'm going to take up an example of lithium because lithium's quite nice. And you'll notice your periodic table has decimal numbers. I'm going to go ahead, just for argument's sake for the moment, round them up or down. The two numbers you end up with are 3 and 7. What that means is the atomic mass relative atomic mass is always equal to the massive, the bigger number. So in this scenario, the relative atomic mass is actually 7, whereas the atomic number, or the proton number, is equal to 3. You may be wondering, why is this useful? Why on earth are we doing this? Well, the fact that we've worked out these two numbers, it can really help us in determining the number of protons, the number of electrons, and the number of neutrons in lithium. Start with what you know. You know that the proton number is 3. So I'm going to go ahead and chuck a 3 in here. This tells me lithium atoms have 3 protons. This is an atom, it's neutral. It's not a charged particle or a charged species. So that means that the protons must equal the electrons to cancel out. If I have plus 3, to cancel it out, I have to add minus 3. Okay? So that means we have 3 electrons because they cancel out. And finally, to work out the neutrons, well, let me remind you that the atomic mass is equal to protons and neutrons, whereas atomic number is only the protons. So if you subtract the atomic number from the atomic mass, you'll be left with the neutrons. And I guess a formula for this would be atomic mass, relative atomic mass, take away proton number or atomic number. In this situation, 7 take away 3 leaves us with a 4. So the number of neutrons in the lithium atom is 4. What I'm going to do in this stage is, if you're watching live, I'm going to put some questions up for you to try out. And if you're not watching live, you may want to pause the video once the questions are on screen, try them out, and then play the video for the solutions. So I'd like you to go ahead and try oxygen. And I'll add in the numbers for those of you who do not have a periodic table to hand. Nitrogen. Let's do potassium. Let's try aluminium. Chlorine. And I'm going to do something cheeky here and round, which we shouldn't do. You must never, I'm going to make a note of that. Do not round numbers in the periodic table. You use whatever you are given in your exam, and in my example, I've given you the values. This is a rule for life. Let's try boron. Sulfur. finally, I'll give you vanadium, transition metal. You have 3 minutes. Okay, so the answers should have been 8, 8, 8, 7, 7, 7. We would have had 19 protons, 19 electrons, leaving you with 21 neutrons. 13, 13, leaving you with 14. 17, 17, leaving you with 19 neutrons. And next would have been 5, 5, 6, 16, 16, 16. 23, 23, and that leaves you with 8, 28. So that's just a flavour of how to protons, electrons, neutrons. And you can practice. There's a worksheet in the description which you can download and you can practice if needed. Now I'm going to move on to the next bit. And the next bit is quite good for using the periodic table as a cheat sheet. Electron shells and outer shell. So we mentioned previously that the atom is arranged with different shells. Let's go ahead and draw that again for you. The first shell, the second shell, the third shell, and the fourth. And the part we need to know is there is a nucleus in the middle, and each shell has a specific number. So the first shell inside is called N, N representing the number of shells, or the shell number, 1. The second is obviously going to be N equals 2, the third, 3, and finally N equals 4. And that's how we can refer to different shells. And you will need to memorize how many electrons fit in each shell as a maximum. So I'm going to go ahead and draw a table very quickly here, which is the shell, N, and the maximum number, I'll make this a bit bigger actually, so we have a bit of space, number of electrons that can fit in each shell. N1, 2, and 3. You need to memorize 2 electrons max in the first shell, 8 in the second, and 8 in the third. And on that note, quite a useful thing to do here is to, I'll show you in a moment actually, to use the periodic table to your advantage. Now, what this means is when we're counting the number of electrons in each atom, there's a simple way rather than drawing, which we call the electron configuration, or the electron number at GCSE. To do this, it's quite straightforward. If we go back to our example of lithium, the number of electrons in lithium are 3, which means if I drew lithium out for you, you'd start with Li, and the first shell would have a maximum of 2 electrons before it becomes completely full. Which means the next electron, the third electron, has to go onto the next shell, number 2. Now, it will get quite easy for you in the long run to start drawing atoms out, but the electron configuration is quite straightforward. What you do is you write the symbol, and you literally state the number of electrons in each shell, separated by a comma or a dot, a full stop. So in the first shell we have 2 electrons, full stop, and the second we have only 1 electron. And that right there is the electron configuration. Next, we have calcium, and calcium is 20 and 40. I will give you 1 minute to work out the electron configuration. Off you go. Calcium has 20 electrons, which means if we follow the above pattern, there are 2 electrons in the first shell, leaving 18. We then have 8 in the second, maximum. We've used up 10, we have 10 electrons left. The third shell has to have a maximum of 8. We now have 18 electrons used. And finally, 2 more, which adds up to 2882. That is the electron configuration for calcium. We'll do one last one together, which will be fluorine, 9 and 19. Total number of electrons are 9. And 2 on the inside, which leaves us with 7 on the outside. In each of these examples, the outer shell, which is the important part, the outer shell, also known as the valence shell, contains electrons that can be involved in bonding. So really important here, it's only the electrons on the outside which would be involved in bonding. So lithium only has 1 valence electron, calcium has 2, and fluorine has 7. More about that in another lesson about bonding, but for now, that's all we need to know. So, the next section I want to move on to is ions. And we're going to start pulling everything we've learned together. And to begin with, we need to understand what an ion is. An ion is an atom or molecule that has lost or gained electrons to become charged. So we're going to go back to lithium yet again, only because I think continuity makes sense. A lithium atom, if you remember, had 3 protons, 3 electrons, and the neutrons aren't important here, but I'll throw them in just for argument's sake. The protons and neutrons are balanced, which means there is no overall charge. And so it's neutral, the overall atom. But what happens if we lose an electron? So for example, if I had Li plus. Well, the first thing is that in terms of the structure of this atom, it is far easier for you to lose electrons on the outside of the atom than it is to lose protons or neutrons from the middle of the nucleus. And in fact, in chemical reactions, the protons do not change, only the electrons. So what does that mean in English? That means the protons in lithium will not change, they will still be free. The neutrons do not change, but the electrons have changed to give an overall charge of +1. And the only way to do that is to lose an electron. Now in this situation, this is like saying +3 minus 2, which equals +1 overall. And the key thing here is the electrons do not equal the protons. That's what this symbol here means. And therefore there is an overall charge, which is what this ion is, Li+. So now your turn. Could you work out O2 minus? And actually on this first one I will help you out because it probably does make sense. I'll just go back and draw O816, and I want you to think of it as a 2 negative charge. Start off by working out the protons, which should be quite straightforward, a smaller number. 8. Neutrons are 8, but the electrons have changed. It may help if we do this. +8. What can we add to +8 to get -2 overall? Well, we need -10. And the only way to do that is to have 10 electrons. So 2 minus actually means this oxygen atom has gained 2 electrons, which are negatively charged. So that is the correct ratio of protons and or correct number of protons and electrons in oxygen 2 minus. What would the electron configuration look like? Well, if we have 10 electrons, the first shell, start by drawing the symbol and the charge, O2 minus. We have 2 electrons on the inside, followed by 8 to add up to 10. Normal oxygen, on the other hand, would be 2 and 6. Next one is for you. If you're watching live, have a minute. If you're not, pause the video once you see the next question, which is magnesium, 12 and 24. Protons, electrons, 12, 12. And then neutrons are also 12. Let's go across to Mg2 plus. We've lost 2 electrons to get 10. Job done. Which means when we're drawing out the electron configuration, Mg2 plus, keeping us 2 and 8. Job done. Now I appreciate a lot of what we've covered today isn't groundbreaking, and for many people, you're thinking this is quite easy and quite straightforward. That's a good place to be. But we need to make sure that there are no misconceptions going forward. You can practice away on ions in your own time, which leads us to a last section on isotopes, which can get quite tricky. It's a word you may not be familiar with, but essentially what isotopes are, they are atoms of an element that have the same number of protons but a different number of neutrons. A few things about that. Chemically, they are very similar. They undergo similar reactions, they undergo similar reactivity, and similar properties even. Where they are different is their mass. So their relative masses are different. I'm going to give you a famous example, which is carbon. Now, carbon, there's actually 3 isotopes of carbon. You can get carbon 12. From now on, we're going to call that C12. You can also get carbon 13. And there's radioactive carbon 14 as well. They are the 3 isotopes of carbon. If you've ever heard of a process called carbon dating, where people and scientists are able to work out the age of an object, maybe something like a fossil or any kind of organic matter, it's using carbon dating, which is to measure the amount of an isotope of carbon. In this example, carbon 14. If we went ahead and looked at the number of protons, electrons, and neutrons in each of these, what we'd find is, firstly, the proton number is 6. So there's no change there. They all have the same number of protons. When they are neutral, they all have the same number of electrons. But now where they differ is carbon 12 has only 6 neutrons, carbon 13 has 7, and carbon 14 has 8. Nothing groundbreaking again, but you do need to be able to work this out. Next example, hydrogen. And we get H1, known as hydrogen. You won't have to memorize these names, but I'm going to give them to you anyway. Hydrogen 2, known as deuterium. And finally H3, which is known as tritium, which is again radioactive. And you can very quickly work out protons, electrons, neutrons, and 1, 1, 1, 1, 1, 1. Differences are 1 neutron, 2, sorry, I stand corrected, 0 neutrons, 1, and 2. Because if you subtract 1 from 1, you get 0. Now, if you're wondering how isotopes are used, or where, what kind of questions you may come across, or how we use them, in terms of calculating relative atomic masses, right at the start of the lesson, I told you not to round. Remember up here, we do not round numbers in the periodic table, and there's a very good reason for that. We're going to look at example lithium. Actually, I'll change it to chlorine. Chlorine is probably a better example. Chlorine in the periodic table has 17 as its atomic number, but its mass is 35.5. For a lot of people, that's a problem because you cannot have half a neutron or half a proton. It's just not possible. So it should be, we expect it to be a whole number. The question is why? Why do we have decimals in the periodic table? The answer is isotopes. And I'll run through the example with you of chlorine, and you'll see what I mean. Chlorine has 2 isotopes. The 2 isotopes are chlorine 35 and chlorine 37. Now, different isotopes, you can find different amounts of them. It just so happens that if you, in the universe, around planet Earth, if you've had any amount of chlorine, 75% of the atoms would be chlorine 35 isotope, and 25% of those atoms would be chlorine 37. So, when we're trying to decide the relative atomic mass of chlorine, which one should we use? Should we use chlorine 35 or should we use chlorine 37? And some of you might say actually chlorine 35 because there is more of it. That would still be wrong because 25% of chlorine is not 35. We've got to be aware of that. We've got to be careful of that. So the only fair thing to do is to average and take into consideration how much we have of each. Now, the formula to do that, to calculate relative atomic mass, is quite a neat one. You take the mass of isotope 1 and you multiply it by the percentage abundance, i.e. how much of it there is. You then add the same calculation for the isotope 2. The mass of isotope 2 times by percentage abundance, and that will give you an average value. So let's chuck in the values we have for chlorine as a worked example. The first isotope is 35 times by 75% plus 37 times by 25%, and overall you end up with 35.5 as the mass. That is the reason chlorine is 35.5. There are many other examples, but the key ones for you are chlorine, carbon, and hydrogen. So to finish off today's lesson, we'll work out carbon relative atomic mass. We said that there are 3 isotopes: carbon 12, carbon 13, and carbon 14. This information will always be given to you in an exam. And what you need to know is something like 99 or 98% of all carbon is carbon-12. About 1% is carbon-13, and then something incredibly small, less than 1%, is carbon-14. For this calculation, you're allowed to just use and assume it's 1%. I'm happy for you to do that. Could you go ahead and use the formula to work out the mass of carbon? Relative mass, 12 times by 98% plus 13 times by 1% plus 14 times by 1%, which gives you 12.00, and then if you continue, eventually there's a change in the number. For now, we'll stick to 2 decimal places of 1 decimal place. And that is why carbon has a mass, a relative atomic mass in the periodic table of 12. That brings to an end this tutorial, which covered quite a lot. You will need to be able to mix and match. And although it does start off very basic with stuff from Key Stage 3, it's important we cover the basics, because the next session we run will be using this information in bonding, which gets quite interesting, but it can be quite demanding. Okay. Make sure you like and subscribe, and feel free to share. Videos will be online, and next time we're online, you'll be made aware. You'll get a notification. Thank you for tuning in, and I hope you find it useful.